So thanks for joining. My name is Didier. I'm the technical lead for the HP Dev community. Together from the team is also Frederic and Denis. They will help with the session here and the questions. Today we have a session, a meetup for May. We started this program more than 2 years ago now as a monthly meetup. And very pleased today to have a joint session by HPE and Red Hat. We'll be talking about GreenLake and Red Hat OpenShift and how you can use that to migrate, modernize, and run your applications smoothly. Before I hand it over to Russell and Jan, I will just do a quick intro for those who don't know the program so much. So this is the HPE developer community. We run those meetups, as I said, monthly. We have upcoming sessions for June and July already in place with registration open. The June session will be delivered by another partner from Thales, a partner and a customer. And the July, and it's about centralized key management with in HPE GreenLake, with a solution that Thales has made available for and certified on HPE GreenLake. In July, we'll have a talk by Jad Abram, and she will be talking about GPU programming in a neutral, vendor-neutral way using Chapel. And it's a session that was also delivered at a Chapel user group meeting recently. We don't have, we have one mentioner for June, which is going to be on June 12th with a talk on digital twins by Cullen Bash from, we had Cullen already talking before from HP Labs. And we have also Galig talking with Cullen, and Galig works for the Office of the CTO. So you can join these. All the links are available for the meetups. It's all under our website, developer.hp.com campaign meetups. And the links are there. And you can find all the replay from our previous sessions as well. The replay for this session will be made available early next week, or maybe Friday if I get everything right. The Munch and Learn, which are different, a little bit different talks, they're all delivered by HPE DTs and CTOs. And CTs, sorry, they are more like thought leadership and talking about technology trends and things like that. You can find all the Munch and Learn, which we started 3 years ago, on that page, and you can find also the replays for the previous sessions on the same page. We also have another way to get additional skill-up capability called our Workshops on Demand. There's a catalog that you can go to on that URL here, and I think Denis will be putting all these links in the Q&A as I speak. We have a catalog of currently 30 workshops. We run all these workshops through Jupyter Notebook Experience. It's available 24/7 to anyone for free, and it's a good way to learn new stuff with some hands-on experience. So we have a lot of 101 kind of training on Python programming, Rust programming, what's a REST API, and then we have more HPE specific trainings or workshops on OneView, on other products. And we have also a few partner workshops. For example, with Red Hat, we have a Podman 101 workshop. We have another one in preparation. Give it a try. You can find also workshops on Docker, on Kubernetes. If you do try, please provide feedback. We are always interested to learn what it was for you, the experience, how you could use it with your customers, your partners, or just yourself. So that's for Workshops on Demand. The rest, just a final word on the fact that this is a community, so it only works with the rest, all of us. So we need you always to amplify and contribute. For example, you can, if you join those talks, you can invite customer, friends, colleagues, students, family members, pets. They're all accepted. Everybody's, these talks are open to anyone. You can join our newsletter. We have a monthly newsletter where you get amplification of everything we do, including those talks, just so you don't miss one. We have a dedicated Slack, which is not the HPE internal Slack. It's a dedicated Slack which is open to customers and partners. So people can discuss dev-related topics, and we have channels for many different things. Feel free to join. We have a Twitter X, or I should say X now, account called HP_developer if you're more like a Twitter type of person. If you're an SME, a subject matter expert in any interesting topic, open source development, anything, we are looking for blog writers or blog authors. We have a system in place to help and making things easy for people to contribute blogs. You can go and check that URL here. We can also have you as a speaker for a meetup or participate in some events such as HP Discover. And finally, you can help us build a workshop on demand. If you are a subject matter in a particular technology, which we don't have today in the catalog, feel free to reach out to us. That's all our channels or touch points. If you want the Slack, we have also an internal Slack, of course, Ask HP Dev Community. You can join that one as well. And the rest is for reference, for sure. You can scan that QR code to get all those links in one single page. That's it for me. Now we can go into the interesting part of the presentation, which is Russell to start with. Thank you, everyone. It's all yours, Russell.
So what I wanted to talk to you about today was to give you some insight into a fairly new product here at HPE. This is the HPE GreenLake for Red Hat OpenShift container platform. Let's see if we can get this moving. But before I go into that specific option, let me just talk about in general what is available at HPE in terms of Red Hat OpenShift. We really have three models in which Red Hat is available or soon to be available. The first option is under the HPE for GreenLake, GreenLake for Private Cloud Enterprise banner. There is work underway at the present to integrate Red Hat to be the choice of the OpenShift container platform, available for customers that are interested in the private cloud for enterprise, which would give them the opportunity to select that as the container platform within that private cloud bundle. For those of you that are familiar with it, the HPE Private Cloud for Enterprise is a solution which comes with really three services: containers as a service, VMs as a service, and bare metal as a service. And as I say, work is well underway to make Red Hat OpenShift container platform be an option within that platform. The second is really where my product comes into play. This is the HPE GreenLake for Red Hat OpenShift. This is designed on standard cloud modules, pre-validated, tested, factory built and integrated, ready to deliver to a customer's environment. And there are a couple of operating models available under this, shared ops models, which allow the customer to choose the level at which the services they're looking for from HPE come into play. And then the third option, and this is probably the one that most people are familiar with, this is the flexible under the HPE GreenLake Flex offers. And this is really where we get to ultimate customization. You know, I've had a colleague tell me this is where the customers can choose the color of their cables if they want to. This is really where anything goes. Customers can design this to meet their exact needs. It does obviously leverage the reference architectures that we have in place, but outside of that, pretty much anything goes. And just to say, obviously, on all of these environments, additional HPE services are available to support the Red Hat OpenShift platform. So I'm going to focus on that middle column. That's the product that I manage. This is a complete solution. It's includes infrastructure from networking, storage, and compute. Obviously, it's factory built and integrated, bringing you faster time to value. managed by HPE to simplify the management and IT operations for your customers, and then utilizes the pay-per-use billing that you may be familiar with in the GreenLake model, and offers in that model obviously offers some level of flexibility where we can deploy more than what the customer needs to begin with. We bill at a minimum commit, and it allows them flexibility to grow up into that additional space as they need it, and then to shrink back down when they don't. So let's take a look at what it looks like under the covers. And I apologize, this diagram is a little bit out of date. That control panel in the middle there is currently represented by 3 devices. It's actually 1 with our latest design. So we have some networking gear at the top. We have a control plane. This is HPE owned and managed control plane. Customers don't have access to that. And that's where we provide our metering, monitoring, logging, access, etc. All that stuff goes through that control plane. We offer options within storage. The customers can choose between Red Hat OpenShift Data Foundation. We have, even within that, we have some options depending on the size of storage that the customer is looking for. And then we do also offer the option for the Alletra. And again, within Alletra, a couple of options depending on storage capacity the customer is looking for. So you can see a 50, 100, 150 terabyte options, as well as a performance option at 100 terabytes. Then we move down to the Red Hat OpenShift control plane. This is a 3-node control plane, and that's where the OpenShift applications itself run, as well as the OpenShift controllers. All of that runs on those 3 nodes as the control plane. And then we have space for the worker nodes. This is a bare metal solution. If I didn't mention that to begin with, let me make sure that that's clear. This is a bare metal OpenShift deployment. This is not virtualized. Although it does support OCP virt, which is obviously virtualizing running inside of it. So the Red Hat OpenShift worker nodes, again, we have some options in this space. We have validated against general compute, memory optimized, and we're in the process of validating some AI optimized cloud modules, which will introduce GPU functionality and allow those customers looking for AI use cases to utilize this solution. This is a scalable solution. So it starts with a small config, which has 3 workload servers. We scale in a minimum of 3 worker nodes, but you can scale that from 3 all the way up to 12 within a single cabinet, obviously power dependent in the customer environment. But this is a validated design that we have. We do currently have designs in place, although not built into our sales tools, so not yet built into OCA and Asset and so on. But we do have designs for a multi-cab solution, with which the first cabinet looks exactly like the full cabinet that you see here on the right. The second cab includes some additional network gear, some additional head nodes to allow for redundancy across those first 2 cabinets for networking and the controller, the Red Hat OpenShift controllers, and then scales up. Our design scales up to 7 cabinets. So what does the service framework look like in terms of this? I mentioned a shared operating model. We offer this as a platform as a service, if you like, the closest as a service description that I can think of, where HPE will manage the hardware platform, we'll do the initial deployment in the factory, we'll do the configuration, and then we will deliver that to the customer environment, finalize all the config, and then hand that over to the customer. And HPE will continue to then own all of the things that you see in green. We will manage the infrastructure and the OpenShift application, leaving the customer to be able to focus on their own application lifecycle and development of that. There is definitely some overlap, some shared responsibility in this model for managing users and also managing the user clusters. HPE will own and manage the master cluster, but user clusters will be managed by the customer. Although, of course, if they ask us to do it, we'll create them for them. But final responsibility will rest with the customer, as they will have full access to those clusters. I'm going to touch briefly then on the flex model. So let me go back one. So that's pretty much the overview of the HPE GreenLake for Red Hat OpenShift container platform. That is the product, as I said, that I'm responsible for. And if we go back to that initial slide where I had the three different columns, I'm going to jump to a second to really the last column, or indeed any of the other columns with the addition of managed services from HPE, just to give you some idea of what management options are available really across the board. So the managed services team do offer management for OpenShift in any of these buckets in which we sell this. And that is the option to then step above what I showed you previously, so above the platform, and actually bring management capabilities right into the dev workspace, up to and including dev onboarding, pipeline management, project setup configuration. In fact, all the things that I have listed there, I'm not going to read them off to you one by one, but plenty of management capabilities available from our managed services team. With the product that belongs to me, we have integration with GreenLake Central, the standard things that are expected from that. So usage, capacity management, and billing all come through GreenLake Central. And in terms of the customer experience of the container platform, that is a simple redirect directly to the Red Hat user interface. So we're not raising up capabilities from the Red Hat environment into GreenLake Central or indeed GreenLake platform. We are leaving all of that expertise and that capability in the Red Hat platform itself. But the things that we are raising up to GreenLake Central, as I say, are usage, capacity management, and billing. My important slide to show the long-term relationship between Red Hat and HPE. I'm not going to spend a lot of time here. I'm sure everybody here is familiar. We have a long-standing relationship between our organizations and plenty of collaboration, and we look forward to continuing that in the years to come. So in summary, what we have on offer from HPE is a quick to deploy, fully managed, comprehensive solution available for OpenShift that really allows customers to focus on their core competency of application development and application lifecycle management. And that is pretty much all I wanted to take you through to share the awareness of this product. And now we can get on to the really interesting stuff where we can start talking about that.
Thanks, Russell. Before we do, we have a quick poll you wanted to run against.
Oh, yes, please.
Okay. So the first thing is that this is actually an amalgamation of a number of different sessions that we do. And the reason for that is there's a huge amount of technology that underpins what OpenShift is. And the technology is often very, very contextual to the people you're talking to. For example, if I was talking to people that had a massive legacy estate, I would focus specifically on virtualization. If I was talking to data scientists, I would focus specifically on the artificial intelligence capabilities. What I'm going to do today is fire you through as many of these developer-centric components as I possibly can, just to get you to have an understanding of the capabilities of the system. And again, if there's anything you want to go into in any more depth, we're more than happy to do individual sessions with you or you and your customers in terms of the individual aspects. So the first thing really is, what is OpenShift? It's a terrible name. Absolutely terrible name. I've been asking Red Hat to change it for 8 years, but the option we normally have is Red Hat Enterprise Kubernetes, which is REC, and we don't want to send anything that actually sounds like REC. But Kubernetes is hard. It's a simple concept. It's a simple concept, Kubernetes, but it's complex in the way that it is actually ultra configurable. And in addition, it's also security agnostic, because it was designed to run on secured platforms, which means that when you're actually installing or using what we call vanilla Kubernetes, and there really isn't any such thing as vanilla Kubernetes, you're the ones that have to actually secure the underlying platform. It's a framework. There's very DIY approach with Kubernetes, especially around adding things like authentication and logging and all those sort of additional dev toolings that developers need. And it's not enterprise ready at all. And as I said before, there's no such thing as vanilla Kubernetes. The minute you install Kubernetes and add your own authentication or add your own logging, you're maintaining 2 different components, 3 different components, 8 different components, all with different release cadences. So OpenShift is, and always has been, well, since version 3, enterprise Kubernetes. And it was designed explicitly to make Kubernetes easy and safe to consume. I didn't do my introduction because we haven't got a huge amount of time, but I used to work for the government. I used to work for GCHQ for 20 years. And my job was breaking systems. My job was actually going in and taking systems down and apart. And the whole point behind OpenShift is we designed it with that kind of person, with me in mind, to stop people like me doing that kind of thing. But we also extended OpenShift to be developer friendly. OpenShift 3, in fact, OpenShift 2 was very, very Java-centric. And OpenShift 3 didn't even have an administrator user interface. It only had a developer user interface. We're currently on OpenShift 4, which is the best of the OpenShift versions, of course, so far. And it was built specifically on a number of requirements that were generated from our actual customers. Deutsche Bank were a massive, massive user of OpenShift 3, and they generated a huge amount of requests for different things, easy to administer, developer features, which all made their way into the final OpenShift 4 product. Now, you need to understand what OpenShift is before we carry on, because at the end of the day, OpenShift and Kubernetes are both object-based desired state engines. And this is what I was talking about when I said Kubernetes is actually simple. OpenShift is built on top of Kubernetes, and all it does when you're interacting with OpenShift is it provides an API for the creation, modification, and deletion of objects. That's all it does. That's all the control plane does. You talk to the control plane, you send a declarative request, which says what type of object you want, or delete, or what type of object you want to delete, or the change of state of an existing object. And how it actually works is in the back end with the worker nodes, which I used to call buckets. These objects are realized if they have physical presence as pods on worker nodes. But the interaction that a user has, that a developer has, that an administrator has with OpenShift is always through that API, and you're always asking for the desired state of something. The architecture and design is simple. It's become much more simple over the years. We have what's called a control plane, which has 3 boxes, and they actually each host the API that you talk to make state changes or create objects. They have a shared clustered data store called etcd, and that's why we have 3 control plane boxes, which we refer to as the brain. The control plane and the worker nodes themselves all sit on an internalized software-defined network. So that's completely invisible to the outside world. And the worker nodes have a tiny robot on them called a kubelet, which responds to state changes or object creation or deletion events from the control plane itself. And the job of the kubelet is to maintain the pods that run on the individual worker nodes. And as I say, it's a desired state engine. So when you ask it to do something, it will actually resolve the state of the object and then keep that object in that state. So, for example, if you ask it to create a pod, the pod will be created. If the pod fails at any point, if it reports itself as not being healthy, it is removed, and OpenShift will reschedule it and put it somewhere else. And it will keep rescheduling it until that pod reports itself as being healthy. It's something called the reconciliation loop that we'll get onto in a second. So, as I said, it's a desired state engine. All interactions with OpenShift are declarative requirements of state. The control plane receives these requests, alters the desired state in the system, in the brain itself, then tasks worker node to realize these requirements. At any point, if any of the components are not healthy, the control plane can task other worker nodes to instantiate them. And this abstracted approach is called what we've named the reconciliation loop. So what's an object model? And this is the critical thing behind OpenShift, because everything in OpenShift is an object. Even OpenShift itself, the nodes, the machines, the software-defined network. And OpenShift works with objects as currency. And as I said, when you interact with the control plane, you request to create new instances, edit existing instances, and remove instances. And how it actually does it is the control plane consists of a number of applications called controllers, which are simply while true loops. And each of these while true loops owns an object type. And what happens is when you send a declarative statement into the control plane to create, delete, or modify the state of an object, it generates an event that are passed into the controllers. If the controller owns the object, it takes that event, processes the event, and then it carries on. The actual event itself is terminated by the updating of the state in etcd. And then if any reconciliation is required externally, i.e. in the physical side, it'll task a kubelet on a worker node to do it. Now, the lovely thing about all of this is that every object within OpenShift can be represented as YAML or JSON if you want. And this gives you pure code as configuration. It also gives you quite a simple API, because all the API entails is you throwing a piece of declarative YAML at the control plane itself. And on top of that, because OpenShift has been designed to be enterprise strength and secure, it applies a strict role-based access control model to the actual objects themselves. In fact, it's not just the objects, it's the actions of the objects. Each controller exports a number of verbs that can be applied to the action. And then the RBAC model in OpenShift allows you to control who, in terms of users, groups, and service accounts, can actually interact with each of the actions. And the beautiful thing about it, and this is what makes OpenShift powerful, this comes from a company that we acquired called CoreOS, is the ability to extend the object model. And when we talk about extending the object model, what that means is increasing the lexicon, adding additional new objects into the number of objects that are understood. And as I said, the control plane works by running multiple while true loops that own and respond to individual objects. And what this thing, which is called the operator framework, does is actually allows the extension, new objects in the model, using standalone custom controllers. So you write your while true loop, which actually exports, I own this object, here are the verbs I can apply to that object. And then the control plane, when it receives an event that's specific to the new object, passes that event out of the control plane and into the operator. And they behave identically to the controllers. They maintain a while true loop, they process event-specific events for the objects that they provide, and they execute the reconciliation loop. And this is the beauty of it. In fact, everything in OpenShift that we're going to talk about, including OpenShift itself, including things like serverless, virtualization, it's all executed by operators, and it's all offered as additional objects into the OpenShift control plane. So that was a very, very quick overview. I thought you needed to know basically how the thing works under the covers. And we're going to switch to the developer viewpoint, the developer side of this. I am a developer. I've been a developer for absolute years. I used to get told off by the CAMs I work with, because I would go into a customer and say, well, I would give my left leg for OpenShift 20 years ago, because it solves so many distinct problems I had as a developer. Specifically something called the 70-30 split. And the 70-30 split is that when you're employing a developer to write code, on average, a developer will spend 70% of their time not writing code. They spend 70% of their time doing boilerplate, doing configuration, setting things up. And what you want to do is reduce that amount. And what OpenShift does is it gives you a tool which basically makes the developer's life easy. They don't have to create hardware. They can just run their applications within the system. It's all controlled for them. The build process, the pipeline process, all those things are actually part of the core product itself. So a developer just sits there and develops, which is the whole key behind it. So as I said, with interacting with OpenShift, under the covers, when you interact with OpenShift as anyone, you just create, modify, and delete objects. And that's pretty boring. And also it's not very fun from a perspective of someone using a system. So OpenShift has two distinct user interfaces that it offers, and also a useful object-based CLI called OC, which is based on kubectl. But the two user interfaces are the administrator viewpoint and the developer viewpoint. They're both reachable from the same entry point. When you go into it, there's something in the top left that allows you to flick between the two. Now we're going to talk about the developer viewpoint. I'll cover the administrative viewpoint very, very quickly. The administration viewpoint is a drill down of the object model. And that's basically what it is. You get a full list of the objects that you can see. They're grouped by types like network, workloads, and all those kind of things. You can actually drill down into them, right down into the individual objects. You can edit the YAML. You can look at the metrics, the logs, and all the observability for the individual objects themselves. But it is a pure drill down object-based model. And as such, you need to understand Kubernetes. You need to understand how Kubernetes hangs together, what the impact is of changing those objects, interacting with the operators and such. What the developer viewpoint is an opinionated user interface designed to assist the developers in interacting with OpenShift without having to know anything about Kubernetes. So it offers things in a more developer-centric way. And it works, as the majority of our systems do, as a left panel navigation, right panel content drill down model. You can see on the right-hand side, we have something called a roundel, which is a round icon, which gives you an instant indication of the state of your application that you're running. We'll talk about applications in a second. And again, the administrative viewpoint provides a more Kubernetes-centric drill down. In fact, the administrative viewpoint was based on Tectonic, which was a user interface that was written specifically by CoreOS when we acquired them. So the concept of an application, it's an overloaded term, and it annoys me personally because we have a number of different applications, or a number of different, slip of the tongue, a number of different products that use the terminology application. But from an OpenShift perspective, the application refers to the components that make up a workload. And it can be as small as a single pod. You can have a pod that's built from an image. You can have a tiny bit of configuration on the side. You can have routes. You can have services. But it can scale up to be a number of disparate objects that make up the composite application itself. The pod, the build, config, deployment, secrets, config maps, and all those kind of things. And OpenShift uses a grouping called a project, which acts as a bucket for these objects. For those people who've got experience with Kubernetes, it's the same as a namespace. In fact, it is a namespace object with extensible and immutable different types of combinations of labels and annotations, which are the extensions that we provide in terms of the objects. The project is a much more formal and fixed way of doing things in terms of controlling what a user can actually do and what they can actually physically see. OpenShift uses an extensional approach with the objects themselves. So it provided, and this is one of the things that we fed back into Kubernetes originally, you can apply labels and annotations to objects, which allow OpenShift to group them and apply functionality accordingly. For example, when creating an application, all the objects will have a label for name, which is essential, which is a required thing, which gives a way to actually indicate that they're contributions to the same application. And makes it simple to find and edit appropriate components and stuff like that. Again, everything is extensible from an object perspective in OpenShift, including nodes and machines, the actual physical architecture, using labels and annotations. In fact, we use the labels and annotation systems as part of node placement. Now we have other things like taints and tolerances, so we can control where applications land within the system, or we can actually provide tolerances that allow an application placement to override the definition of a taint. So there's some very clever stuff that goes under the covers that uses labels and annotations. Going to talk about builds very quickly. So we have this concept of what we call in-cluster image building. And if you're using a container runtime host, let's say you grew up with Docker or you use Kubernetes, they both execute containers and or pods from an immutable image. And this image is actually, it's quite funny because images don't actually exist. And I know that sounds like the COVID speaking, but the image is actually a hash map to a set of file differences that are implied in order on top of a base file system. Containers are file systems with delusions of grandeur, literally. And what you do is you build from a base file system, you apply these file differences, and they're defined in order by the image itself. And then you process bind them and execute it. And that's what happens when you execute a container. Now, with normal Kubernetes and containers, it's up to the developer to build that image externally and then provide it. So you get tools like Docker, you get tools like Podman, which is a tool from Red Hat that allows you to build containers and pods locally. And then you provide it to the system to orchestrate. For example, the standard deployment object in Kubernetes consists of an image location, where to go and get that hash table file differences, and a count of replicas to deploy. So OpenShift makes this far easier for developers by providing a number of facilities in cluster to execute and keep up to date an image built from source material. So a developer can actually build source on OpenShift itself. We've got a tool called DevSpaces, which provides an in-cluster IDE for building source, or they can pull source from a Git repository. And then OpenShift can physically build that into an image and then use that composite image as the application source. And all build orchestration is done within the cluster itself. It uses pods. So it fires up the pods themselves. The pod will go and pull the base image. It will pull the physical code for the application. It will do a binary build. It will build a composite image. It will deliver that composite image into the registry. The registry is a bank of images within the actual system itself. Now, we've recently introduced something called builds. Builds is incredibly useful because for a long time, OCP supported source to image. And source to image was an external application. You could run it externally, but it was executed within the cluster that would take a framework base for an image. It would clone target source. It would execute a binary build. It would produce the composite image. But there were a couple of gotchas on that. And that was, well, the first one was that it was originally called STI, which got a lot of laughs in meetings, especially when I was dealing with the army. But the other problems were that you had to run it as root. And the other thing was that it used to write the source material into the output image. So the image would come along with the binary components, but it would actually write the source image into the source material into the image, then compile it, and then produce the whole lot as an output image. So there were some security implications of having an image that you deploy to a container that had the source within it. So this has been simplified now because there was an external community project called Shipwright, which basically handles all the builds you need to build images, but it does it in a contained way. It uses a tool called Buildar, which allows you to actually build an image without having to be root. Now, in the old days with Docker, you had to be root to build an image because of the way it would map the file systems in order to build the composite image. So the whole concept of the source to image and the builder and all those things has been packaged into this new approach called builds, which is actually distributed as an operator. It's a free supported operator as part of OpenShift. You install it, and then you simply throw pieces of YAML defining the build into the system, and the operator for builds will execute the build for you. So it's a very, very nice feature, and it's reasonably new. It's called Builds for Red Hat OpenShift. Serverless deployments. Now, I've got to calm down a bit because this is my favorite technology at the moment. It's a bad name. Yeah, I always get told off when I talk to customers. I talk about, and I describe how badly named serverless is because it is a server. It's just someone else's server. Kubernetes, as I said, is a desired state engine. And what this means is that when you deploy an application, it remains resident at the state you asked for until you request the state to change or you remove the object. And for the majority of cloud applications, occasionally called applications, highly inefficient. I used to give an example of this. So let's say you've got a system that's made up of 10 microservices, and each microservice is hosted as an individual container, which is a fair enough way of doing it. It's a proper way of doing it. You're building these kind of sausage machines. When you deploy those 10 microservices, you get 10 containers, 10 pods running 24/7. They sit and they run and they wait for requests to actually be used. So your system where you're actually orchestrating these has to stand up these 10 pods. And those pods just sit there doing nothing. And let's say 9 of them are called once every 24 hours and one of them's called every 100 milliseconds. So the one that's called every 100 milliseconds is getting used. And the other ones are sat there just doing nothing, just consuming resources, just ticking over CPU cycles until they actually get a call. So what serverless did was it introduced the concept of what we call on-demand execution and resource consumption. And it should really be called server when you need it, but that's too long. And the way it works in terms of the on-demand execution is that, and it's an incredibly simple way of doing it, it provides the ability to deploy applications that scale down to zero. Now that sounds mad, well, you can do that right now with Kubernetes. You can go in and set the number of replicas to zero. But when you do that, it leaves the ingress point for traffic there. So when you send traffic in, you get an error. You get can't route traffic to the actual thing. So what we do with the serverless is it retains an ingress point. And when traffic arrives there, if the application isn't active, it spins it up and then sets a timeout. When the timeout expires and no traffic has actually arrived, it spins down again. When an application is scaled down, it consumes no resources. And more importantly, and this is the very important part, it does not contribute to the resource calculations when placing components in the cluster. So there's a concept called node placement, which allows OpenShift to decide where in the cluster it places something. So you can go in and say, here's an application, place it somewhere, and it'll go to each of the nodes, and basically it'll look at what's running on the node, it will get the resource consumption or the resource requirements for the applications, and it will push the actual application to a node that has available resources to run it. With a serverless application, it doesn't contribute to that algorithm, which means in theory, you could deploy 10,000, 20,000, 30,000, the maximum number of pods to the worker node as serverless without consuming any physical resources, because the physical resources are only consumed when the thing starts up. And what's clever about it is not only does the actual ingress controller, which spins up the application, bring it up from zero if it's at a point of zero and you receive traffic, it also makes sure that the worker node can cater for it in terms of resources. And if it can't, it's automatically rescheduled somewhere else. So you've got this ability to overcommit your system. And also, and this I get told off by the Red Hat salespeople when I talk about this, you can have much smaller clusters because you don't have all these applications hanging around waiting to be used. Very quick on the serving mechanics. So you define a Knative serving. So Knative serving is the backing technology for this. It initially deploys without traffic, giving the settings defined in what we call a configuration. So there's a configuration option that tells the application how it's meant to be pushed out. Upon healthy deployment, it will then scale down to zero. And you can actually set these up with a configuration that says don't scale down to zero, because you can use this for actually doing network traffic-driven scaling. When traffic arrives at a route, which our route is another object that's offered, it is forwarded appropriately to revisions. Now, a revision is the latest version of the configuration. If you change the configuration, let's say you change the image or add an environment variable, you get a new revision. Revisions are immutable. And they're kept as an audit, but you can also scale traffic to them depending upon the revision. So you could have a newer version of the application, which gets 10% of the traffic through the serverless mechanisms. If an application is scaled down to zero replicas, it is scaled back up according to the behavior stated in the configuration. A timeout is then started, so you set a timeout on it. If no further traffic arrives at the route before the timeout expires, the application is scaled down according to the configuration. So this allows you, and the major selling point I got when I'm talking to customers about this, is you can take a fully functional, massive legacy application, you can break it down into microservices, and then you can run those microservices as serverless components. So you've got an application that's 1,000, 2,000, 3,000 individual microservices, each doing atomic components of that application. And then by deploying them as serverless, only the ones that are actually being used at any point are actually consuming resources. So you can get very complicated applications into much, much smaller resource consumption spaces. It's an incredible technology. It also has this concept called eventing. And eventing allows you to do effectively the same, but instead of being driven by traffic, it gets driven by events. And there's this overall new approach to events called cloud events, which is a specification that's being created for simplifying and unifying events within a Kubernetes cluster. And what happens with the Knative eventing, which is the eventing side of the serverless, it provides the ability to hook the concept of serverless into event-driven capabilities. In fact, it's not like serverless and it actually provides ingress controls and things like that. Eventing provides a number of APIs that you can write applications to adhere to. And it provides an API for routing events from producers to consumers. Consumers are also known as sinks. These sinks can also be what is known as brokers, and brokers are basically the ingress point where the events arrive. So you can set up brokers, you can throw events at the brokers. These brokers can be backed by things like Kafka. These events are then pushed out using triggers to individual serverless components. So going back to the example we said about having thousands of microservices, you can now have that, but instead of having the APIs calling each other directly, you can have the whole thing driven by events. And you get the advantage of having very, very small resource consumption and dynamic on-demand resource consumption because you're using serverless under the covers. Making it easier for developers. Again, I'm firing through this because we've got loads and loads of stuff to talk about. There's too much pressure for developers nowadays. When I was growing up, when I was a developer, there were like 4 or 5 languages. When I started being a developer, there were 4 or 5 languages to choose from because I'm much older than I look. Nowadays, a developer's life is incredibly tough. And to describe it, we talk about something called cognitive load. Because a developer wants to develop. That's what we want to do. We write code. But technology has become so varied and complex at the moment, it's hard to just write code. If you're thinking all the time about the framework, the boilerplate, the patches, the environment, you're hard-pressed to find brain space to think about elegant, efficient code solutions. And the key goal with this is to reduce the effort and unnecessary thought processes a developer has to have when they're writing code. And again, I mentioned earlier the 70-30 problem split. Nowadays, it's even worse. Most developers have a problem even starting because there's so much variety of what you can do. The solution is something called an internal developer platform. An internal developer platform is built by a platform team to enable developer self-service. And it provides, amongst other things, a hub, which is a single point the developer interacts with that has all the tools, guides, documentation, and access to the environment that a developer needs. It provides guided and supported paths to success called software templates. And it provides a simple and easy to use, less cognitive load mechanism for producing software itself. We've got something called Red Hat Developer Hub, which is based directly on Backstage. It's a version of Backstage. It's a branded version that has a number of Red Hat extensions built into it as plugins. And the beautiful thing about this is that it is pure Backstage. And what we mean by pure Backstage is that it can use all the plugins that are out there for Backstage at the moment. Plugins actually extend Backstage. They provide additional user components that can be offered in that single point portal, which is the IDP, and they provide functional things that can be called, which generate software or interact with software. They take away the mandronic or the nugatory things that a developer has to use. And when you're using things like this in Red Hat Developer Hub, you create 2 distinct personas. The maintainer who configures the server-side Red Hat Developer Hub, and the consumer who works with the portal that's actually provided. With Red Hat Developer Hub, what we've done is we've provided this simple tool you can add into OpenShift that provides a very easy interface for administrators to build an IDP and a very easy endpoint for developers to consume it. I'm going to talk very quickly about pipelines for developers. So we've got the ability within OpenShift through OpenShift pipelines using a new technology called Tekton to actually do pipeline behavior. In the old days, this was down to Hudson and Jenkins. And in the old days with OpenShift 3, we had a tight integration with Jenkins. So you could run developer pipelines from within OpenShift, but it would pass control out to Jenkins. Now, some clever person came up with the idea of Tekton, which is actually objects you can build pipelines with and control the execution of pipelines, but they're native Kubernetes objects. And it's a fantastic way. And the beautiful thing about it is that these pipelines you build can automate any Kubernetes objects. So you no longer just do builds and things like that. You can do all your day 2 operations, things like adding new users, setting up appropriate project spaces. all through Tekton, all through OpenShift pipelines. I'm going to skip over this because I'm running short of time. I want to get these last two things out. Every man and his dog wants a chatbot at the moment. Don't get me started because I did proper artificial intelligence for 20 years, and GPT is a plagiarism engine, but everyone's screaming for it. Well, we've got this concept called OpenShift AI, again added as an operator into OpenShift, which gives a composite and integrated set of data science tools. And in fact, IBM Watson X, which is the next gen pitch from IBM itself, runs on top of OpenShift AI. OpenShift AI is installed as an operator. It abstracts a data scientist away from Kubernetes, gives them all the things they need to build and train and host models. And finally, and this is the stuff I really wanted to talk about, legacy application with virtualization. So OpenShift now out of the box, a worker node can execute virtualization. Any of the instances of OpenShift, OKE, OCP, as long as they're running on bare metal, can run supported virtual machines. Now, when I looked at it, I thought virtualization in containers doesn't make sense. Containers are file systems with delusions of grandeur. Virtual machines are composite machine images you have to execute directly on the kernel. How does that work with an orchestration system like OpenShift? Well, what it does is incredibly cool. It allows OpenShift to execute virtual machines natively on the kernel of the worker nodes. So it's just doing virtualization. And it's old school technology. It's KVM technology. It's technology that's been mature for 15 years. But instead of having a centralized control point like vCenter or a control plane for executing, standing up, monitoring the virtual machines, every virtual machine has its own pod, which acts as a microcontroller. So when you create the virtual machine, when you migrate it, because you can do live migration out of the box with any of it, when you change the configuration, when you interact with it through the software-defined network, it's all controlled through the pod itself. There's a tiny pod which acts as an ingress point and acts as an API controller for the virtual machine. What this means in English is you can lift and shift your legacy applications that are running as virtual machines today. And we've got a toolkit called the Migration Toolkit for Virtualization that does it for you. And you can execute them on OpenShift. And because they're actually executed and accessed through a pod, you get all the advantages of a pod running on OpenShift. Single security model, RBAC controls, SDN ingress. You also use a technology called Multus, which allows you to mount external NICs directly into the virtual machines that are not exposed into the OpenShift system itself. So you can run up virtual machines that have got access to virtual private networks or secure streaming and still execute them in the same way. Exactly the same behavior profile, same footprint, same speed. And it means you can take someone who's got a legacy estate, they can move it all into OpenShift as virtual machines, and then they can modernize them slowly by actually taking each application out of a virtual machine, containerizing it, and then just changing the software-defined definition to ingress traffic instead into the virtual machine, into the application. It's incredibly powerful. There's a way to get your hands on this for free initially. If you point your phone at that QR code there, it will take you straight to developer.redhat.com. We've got something called a sandbox, which gives you 30-day access to a full version of OpenShift with one project. We've got virtualizations installed, we've got OpenShift AI installed, we've got serverless installed. You can go and have a play with that for free. You can pass it on to your customers as well. It's a very easy way for people to get access to this kind of technology without having to fork up cash up front for it. And that version, the sandbox, has the latest version of OpenShift. And again, I'm about to, what you're seeing there is a learning path I wrote, which tells you how to install and configure Red Hat Developer Hub and have a play with it. I've just written a new learning path that shows you how to create a Fedora virtual machine and then migrate an HTTP application from running within that VM to running in a container. So there's some very, very cool stuff coming. I'm aware that I'm running short of time and my voice is disappearing as well. So I will call it a day on that one and say thank you. And I apologize for that fire hose of information.
Thank you very much, everyone, and talk to you later. Bye-bye.